Hi, I'm Adrian Barker at the University of Leeds, and I'm going to talk a little bit about some of my work in the next few minutes. I'll just load the slides. So the primary focus of my research is on tidal flows in planets and tidal flows in stars, although I also have interests in other problems in astrophysical fluid dynamics more generally. And I'm on the faculty at the University of Leeds in the UK. Just to give you an illustration of some of the problems that I work on, I've given some archive links for some published papers here on the right. So to motivate the general problem of tides in stars, there are several applications I could have used, but I used orbital decay of close-in planets. The idea is that gravitational tidal interactions between planets and stars drive long-term spin and orbital evolution in planetary systems with close-in planets, such as hot Jupiters. These planets that have masses similar to Jupiter's mass that orbit their stars in less than about 10 Earth days. And gravitational tidal interactions also cause spin and orbital evolution in binary star systems as well. And the application I use now, as I said, is planetary orbital decay. So if we detect planets using the transit method, and this is just an example of a transit light curve on the right, for one system called WASP-18. And this system has been detected for over a decade or so. And these transit light curves have been observed over that sort of timescale. And what you can see over that sort of timescale, so the transit is just the dimming in starlight as the planet passes in front of the star. And if you can detect this over a decade or so, you can start to look for slight shifts in the center of the transit. So if the transit is occurring gradually sooner and sooner over the decade or so that you're observing it, then that can be interpreted as evidence of orbital decay of a planet. And there's one system, not the one shown on the right, but the one I've listed on the left, called WASP-12b, where there is some strong suggestions that this planet could be undergoing orbital decay on about 30 milliseconds per year timescale, or in terms of its orbital period changing, which corresponds with orbital decay on about a 3 million year timescale. And there are other systems where rapid orbital decay is not observed, like WASP-18b. So the question is, theoretically, can we understand the mechanisms of tidal dissipation in a star? Because they're what drive these evolutionary processes over millions and billions of year timescales. So from the observations, if we have a constraint on the planetary mass and stellar mass, and the stellar radius and the separation of the system, an orbital period, then we can use the shift in the center of the transit to constrain the mechanisms of tidal dissipation in the star, which we can use to compare with tidal theory. And so that's what the formula at the bottom there is indicating. So what I do is I study tidal flows in planets and stars theoretically using first principles hydrodynamic and MHD calculations, both analytical theory to understand the mechanisms involved, and also direct numerical simulations using a mixture of local models and idealized global ones to study the mechanisms of tidal dissipation in stars. And the results from these are used to predict or explain the properties of planetary systems and binary stars, perhaps using stellar models, for example, using the Mega code. So to understand tides in stars, we need to look at a variety of structures. From fully convective stars, masses less than about 0.4 solar masses, to stars with similar structures to the Sun, they're ready to cause convective envelopes, like M, K, and G stars, and then stars that are a bit more massive than the Sun, have about 1.1 solar masses, that have convective cores at the center, radiation zones, and then thin convective envelopes on the surface. These are usually the types of structures that are relevant for close-in planets. And so that's what I mainly focus on, but you could also talk about even more massive stars than this as well. So what are the mechanisms of tidal dissipation in stars? So the classical one is thought to be the interaction between a large-scale equilibrium tide, which is essentially an ellipsoidal bulge that follows the companion, and it's the flow associated with that. So this is a large-scale quasi-hydrostatic deformation of the star or planet due to the companion body. And it's long been thought that this flow is dissipated through its interaction with turbulent convection. So if we use the laminar microscopic viscosity of the fluid to try and damp this flow, then the equilibrium tide is very weakly damped and there'd be no evolution over the main sequence lifetime of the star. Whereas if you have turbulent convection that can enhance the effective viscosity of the fluid, then that's long been thought to be a mechanism that can lead to enhanced dissipation of equilibrium tides. And this is something that's been studied using phenomenology in the 60s and 70s, but it's only recently we've been able to simulate this. And that's something that my group has been working on recently. And I'll talk a little bit about that in the next few slides. Equilibrium tides can also be damped through instabilities, but probably this is less important to the stars, so I won't talk about that. But there are other mechanisms of tidal dissipation that are important as well. So in convection zones, you can excite waves. And if you have rotating stars, then you can have a type of wave called an inertial wave that can exist in a convection zone. So these waves rely on the Coriolis force for their existence, and they have curious properties. In particular, the wave vector makes a certain angle with respect to the rotation axis, depending on its wave frequency. And you can see that in a figure on the right from a simulation of these waves. And these waves bounce around, preserving that angle, so you have quite intricate patterns when you look at the structure of these waves. But importantly for tidal dissipation, these can lead to a significant enhancement in the tidal dissipation when these waves are excited. But they're only excited if tidal forcing frequencies are less than about twice the stellar rotation frequency or planetary rotation frequency. So they require either low frequency forcing or rapid rotation, depending on how you want to view it, for these waves to be excited. So these are likely to be important in young stars that are rapidly rotating, important in binary star circularization problems, but for hot Jupiter hosts, it's probably not the dominant mechanism for why the orbits of planets like WASP-12 decay, because the stars rotate quite slowly. So I'll talk briefly about that in a few slides' time. And we also have another mechanism of exciting waves, and this is in radiation zones of stars. You can excite G modes or internal gravity waves that tend to be launched from the convective radiative interface, propagate through the star, and then what happens near the center of the star is important for whether these waves are dissipated efficiently or not in stars like the Sun. This is just showing you a result from a simulation I did about just over 10 years ago, looking at these waves propagating toward the center of the star. And it's in the case when a massive planet excited a wave in the star, the wave reached the center, the wave underwent braking, and then deposited its angular momentum near the center of the star and spun the star up from the inside out. So just to give you a flavor of that, these three aspects, if you go to the equilibrium tides mechanism, then I've recently been interested in studying this over the past few years using idealized global and local simulations. So just to give you an illustration of the local simulations that I've been interested in looking at, this is by my PhD student Craig. And what he did is studied really Bernard convection, which is convection between two parallel plates, hot plate at the bottom, cold plate at the top, which is just an idealized model of convection to study the physics of the interaction between tidal flows and convection. And the idea is in this model, we model the tidal flow in a local approximation as being a flow that's linear in the Cartesian coordinates and is an oscillatory flow. And it's long been thought that the oscillatory nature of the tidal flow is important in determining how efficiently it's dissipated by the convection. And there's a long-standing uncertainty about how efficiently the tide dissipates the convection when the tide is fast relative to the convection. So when the convection is slow. So in the Sun, we know that the turnover timescale of eddies at the base of the convection zone is of order a month or so, and the tidal timescale of a one-day hot Jupiter is half a day. So the tide is fast relative to the convection, and it's long been known to be uncertain how efficiently this interaction proceeds in that regime. So my group's recently been involved in doing simulations of that and studying this directly using idealized models of convection. And the idea is we can model this interaction between the tide and the convection by an effective viscosity, which is essentially just a way of presenting the results from analyzing the simulations. And the results of this is you can determine a frequency dependence to the effective viscosity and how this depends on tidal frequency. And there was a long-standing uncertainty about what the frequency dependence is in the regime of high frequency forcing. So on the right of this figure, it's showing you the tidal frequency normalized by the convective frequency. And the red dashed line is just for a one-day hot Jupiter orbiting a slowly rotating star, where their frequency is for a star like the Sun, for the eddies at the base of the convection zone. And as a result of this strong frequency dependence and the fact that the effective viscosity, which is on the y-axis, normalized essentially by mixing their values, so the convective velocity and length scale. At the far right of the figure, the fact that this falls off with frequency is indicating that this mechanism is likely to be inefficient at high frequencies. And if you extrapolate this in stellar models, it indicates that dissipation of equilibrium tides is weak at high frequencies. So this mechanism is not likely to be responsible for the orbital decay of water-12. But around giant stars, this is likely to be the dominant mechanism in tidal dissipation, because the frequencies are generally lower for the relevant regime of interest. This is just a flavour of one of the results that Adrian's recently been working on. Simulations of convection interacting with idealized models of tidal flows. And the same things have been done in global simulations as well. But to just give you a flavour of other aspects of the work that relate more to the Cavity Program project, is we can look at tides in convection zones of stars. This is where inertial waves can be excited in rotating stars by tidal forcing. And these waves can be excited particularly in rapidly rotating stars, but also in the binary star problem, in which you're looking at circularization of the orbits of binary stars. This is often thought to be relevant. And the idea is that inertial waves can significantly enhance the dissipation over cases when you don't have these waves, as is indicated by the figure at the bottom left. So if you're showing an inverse measure of the tidal quality factor, so the larger the values are here, the more dissipative the star is. And this is based on a linear calculation looking at the waves in a spherical shell. And what you can see is that when the inertial waves are excited, so when the tidal frequency is between twice the rotation frequency and minus that, there's a significant enhancement in the dissipation. And what I've been recently interested in doing is looking at how this enhancement depends on the structure of the star, using a simplified frequency average formalism that was developed by Gordon Ogilvie, and allows you to calculate the frequency average dissipation in stellar models in a simple way, building upon some work that's been done by others recently, Stefan Matisse and collaborators. And the idea is that gives you a simple measure of the dissipation in of these waves. So we can study this directly using simulations as well, like in the figure on the right. But if you want to look at tidal evolution timescales, well, the evolution of a star and the stellar properties on tidal evolution timescales, we want some sort of prescription we can take from those calculations. And here I've just taken a single value of what's called a frequency averaged measure of the dissipation, which can be used to compute how this varies as a function of the properties of the star. And this can be done, for example, in mesostellar evolution codes, which is what I did here. And this shows the dissipation of inertial waves in various stellar models as a function of the age of the star. And this can be used to infer tidal evolutionary timescales. And this, in particular, it'd be interesting to apply these to binary circularization, which is one possible project at this Cavity Summer School. So the final aspect I just wanted to briefly mention is internal gravity waves and radiation zones. So on the top right, I've shown the tidal response of a star due to a hot Jupiter on a one-day orbit, showing the velocity of the equilibrium tide, the radial and horizontal components of the tide. And in the radiation zone, you can see that this is primarily oscillatory wave-like behavior corresponding with gravity modes or internal gravity waves excited in the core. And you can see the amplitudes go up as you reach the center. And this is thought to be due to geometrical focusing effect as the waves reach the center of the star. And there's an unsolved problem really about what happens when these waves reach the center of the star, and that determines how efficiently these waves are dissipated. But if these waves are very efficiently dissipated, so for example, if they cause wave breaking at the center of the star, then this can lead to orbital decay of hot Jupiters on timescales of order a few million years. So this is potentially responsible for why WASP-12b is undergoing orbital decay, and it nicely explains that observation, depending on the stellar model, but there's still some uncertainties about that. And in particular, uncertainties about what happens for lower mass planets as well, whether they cause wave breaking as well, which is related to one of the Cavity projects this year. And so this figure at the bottom right was just from a simulation of this interaction. There are many unsolved problems in this mechanism. So I've just briefly introduced tidal dissipation in stars and the mechanisms that are responsible for this, and some of the work that I've been involved with either recently or in the more distant past that relate to the projects that I've proposed for the Cavity program. So tidal dissipation in stars drives orbital decay of planets, such as hot Jupiters. It is also responsible for circularization of the orbits of binaries and in synchronizing their spins with the orbits, so the process of tidal locking. So for the Cavity program, the projects I've proposed, one of them is to look at wave breaking of tidally excited waves in solar type stars, these gravity waves, due to resonance passage. one of the projects is to look at tidal circularization of solar type binaries using inertial wave dissipation in the pre-main sequence stage, in particular using stellar models. And the third project is in collaboration with Aurelia Stool, who's my SDFC funded postdoc. And she has proposed a project on tidally excited inertial waves approaching co-rotation in differentially rotating planets and stars. So project 1 and 3 primarily involve numerical simulations together with some analytical work. And project 2 is primarily numerical, involving stellar models. So please come and chat if you have any questions, or get in contact if you have any questions about any of this stuff.